Welcome to our third Ask an Expert webinar of the year on the topic Smarter Control, Stronger Performance. It's going to go into the unlocking value that we get from closed control loop monitoring. Before we get into the topic today, just some housekeeping items. You will see all of these symbols on your platform. If you have any questions, use the question symbol and we will make sure to answer them in the end. If you have any specific questions as our speaker is going through the content, please feel free to ask and we will address them as they come. If you need to contact our team for any technical issues, you can do that again through the platform. If any additional resources to access that are relevant to the topic today, you can also do that from your platform. If you need to connect with our speaker, you also have the option to do that through this platform as well. Again, technical assistance, you can reach out to us directly, and then we will have a brief survey in the end, just so that we know how this webinar went for you today and how we can better improve in the future. I also wanted to remind everyone that this is a monthly webinar series that we will be running for the rest of the year. The QR code that's here, you can just scan on it and you can register for any of our upcoming episodes. You can also view the on-demand recording for the sessions that have already happened. And with that, I would like to introduce our speaker today. We have Will Doherty, who is the Global Business Consultant Leader at Velotic. And with that, I'll pass it to Will.
Great. Thanks, Arnie. Welcome, everyone. Thank you very much for joining this session today. If you're in Europe, I know this is a little late. If you're in the US, good time. But anyways, what we're going to do today, we're going to go over some of this really cool new functionality we have called closed loop performance monitoring. So first of all, I'm going to do a little introduction on the company Velotic. You might know us as GE, or you might know us as PTC, but we've joined into a new company called Velotic. Then I'm going to go into why control loop performance monitoring matters. What are the benefits of it? I'll go through some use cases. I'll go through some customer stories. And then I'll actually go and do a quick demo just to kind of give you a look and a feel for how our software actually works. And then at the end here, we're going to have some Q&A. So if you do have questions during any of these slides that I'm going through, just go ahead and feed them into the Q&A chat, and Arnie will pick them up and ask them during those slides. So instead of having to wait till the very end, we can kind of take these as they're going. All right. So first up, let's talk about Velotic. So the name Velotic, just think about velocity and analytic put together. That's kind of how the name came about. But basically, I've been with the GE side of things here for 15 years. So you have the same products, you have the same teams, you get in the same support model. But what's happened here is we've actually joined the Proficy suite that you know from GE with some products you're probably very, very familiar with. So on the Proficy side, you have things like iFix and Simplicity and Historian and our MES solution called Plan Apps for Smart Factory, our analytics called cSense. But then we also have, it's coming over from PTC, which is another really big software company. We're taking out some of their industrially focused best software applications. And one of those is something called Kepware, which is in thousands and thousands of plants all over the place. And then this really nice IoT platform called ThingWorks, which does visualization and connectivity and dashboarding, and a whole bunch of different functions. So basically, we're putting all of this together into one company called Velotic. And basically, instead of being part of a huge company like PTC, which really focuses on CAD and PLM software, or part of big GE, which really focuses on, gas turbines or steam turbines or big VFDs or wind turbines, we're really just focused on industrial software, and we're having a standalone company that's just focused. Our whole board, our C-suite, everyone is just focused on industrial software all the time. And given Velotic, what we're basically doing is this is really kind of the challenges that we're focused on as a company, really going through here asset utilization, trying to figure out root causes for downtime. So how to get continuous improvement. So people who are going through lean exercises at their plants and factories, it's really software around industrial operations. Another thing that we're really focused on is getting in production data. So if you know Kepware, what it's really great at is talking to machines. So if you have a whole bunch of PLCs or DCS systems or IoT things that might be talking MQTT or via REST API, whatever it is, how do we get all of the data in from all of these different systems and all of these different sensors and put it into one place where we can actually start making decisions based on that? And then the other side of this is also putting it into a digital format, right? So we're basically allowing operators now, instead of getting paper, they're actually interacting with digital forms. The other nice part about this is if all of your data is held digitally, now it's really easy to say, what happened last time we ran this product? What does the health of this pump look like over the last 5 years? When was the last time we did maintenance on it? What happened the last time we took oil out of that transformer and tried to see what the transformer health was? How does this packaging line compare to this packaging line? So all of those questions around stuff gets a lot easier when you have all of this data in a digital format. You're not going through filing cabinets filled out with paper, right? And then obviously going through and digitizing your production tasks and also going through and managing quality. So how can I make sure that I'm making consistent products and they're always delivered within specification, right? So all of these are kind of the challenges that we're really focused on in Velotic. It's really industrial software, right? That you can go ahead and put on any control system. You can connect up to any business systems. But as far as going through and having your industrial assets focused on some software, that's where we're really focused. All right, so the next thing we're going to go into why control loop performance monitoring matters. And really this is focused on PID loops. So if you do have a factory out there, most likely, even if you don't know it, you have PID loops. And some people know that their whole factory, the most important thing out there is how all of their PID loops are performing and how we can actually make sure that this works well. So I'm going to go through here and kind of do a little bit of just an introduction of what is a PID loop. So if you can imagine that you actually have a system like this, you have a valve here that can open and close. It can open 30% or 50% or close fully, right? You have some gas that's flowing through, and then you have a pressure transmitter that's actually telling you what is the pressure of that gas. So now you could imagine maybe someone says, you know what, I really want the pressure of that gas. This is kilograms per centimeter, but you could do pounds per square inch, whatever it is. But if someone says, hey, you know what, I want the pressure to be at 60 PSI, right? And what they're actually doing is saying, I want the pressure to be at 60 PSI. How much should I open and close this valve to keep the pressure at 60 PSI? And really, if the pressure and the flow coming in is very stable, and then the actual processes that are taking that gas are very stable, maybe you just leave this valve at the exact same position and you get a smooth, even 60 PSI. But what ends up happening is a lot of times the gas flow coming in can change. You can get a lot more pressure coming in, and then I have to close down my valve to control it. Or you can have the process on the backside here taking a lot more demand, right? And then how do I actually increase this valve to actually allow more flow to keep my pressure up as I'm actually moving more volume of gas? So really what you have is you have these things called PID controllers. This is going back to your school days where you actually had, it's called process or, oh my gosh, well, I forget what the P is in PID, but it's integral and derivative, but I think it might be process. But basically you have 3 variables that you're going to put in, and really depending on how your process works, those 3 parameters basically detect or control how well you're going to actually control that process. So a couple of things that we have is we have the set point, which would be like the 60 PSI. We actually have the process variable, which is actually measuring what our current value is. So it might be 60 PSI is our set point. We're currently at 58 PSI. And then you actually have the manipulated variable, and that's basically this valve position. So how much am I opening and closing the valve? So as my pressure drops, I might open the valve more. As my pressure increases, I might close down the valve. So if you think about this in like If you've ever had a car that you're doing cruise control in, right? As soon as I have my cruise control set at 65 miles an hour, if I go to a hill, I want it to push the accelerator. That's the manipulated variable. As soon as I start going downhill, maybe I want it to come off the accelerator so it can actually keep my speed. But because I'm going downhill, the car is now actually going faster, right? So you want to basically make that as smooth as possible. When you actually look at PID loops, there's a couple things that actually happen here. So what I'm showing here is, imagine we have a set point, this dotted line, it's changing from 55 to 65 miles an hour, right? And as soon as you start changing from 55 to 65 miles an hour, you now want your speed of your car to actually get up to 65 miles an hour. You want it to get there smoothly and as quickly as possible. So there's a condition they call overdamped, where basically this is like, imagine you have a really timid driver and they basically barely touch the accelerator. And you do eventually get to 65 miles an hour from 55, but it just takes a long time. The other thing is you have a brand new teenage driver, and what they do is they just slam on the gas, and then they're like, oh, wow, I'm going 70, and they just hit the brake, and they're down to, now they're down to 60, and then they hit the accelerator again, right? Again, this is a lot of oscillation. This is called underdamped. You don't want that either, right? It's a really jerky part of the process. There's another thing called critically damped, which is what is the fastest way I can get to 65, but I also don't want any speeding tickets. So I don't ever want to go over 65, but I want to get there as quickly as I can. So basically that's called critically damped. And then you really have this thing called optimally damped, which is just get me to 65 as quick as I can. You might end up shooting over a little bit to 67, but that's okay. I just really want to get there as quick as I can to the new set point. So this is what you ideally want to have, is either this critically damped based on your process or optimally damped are the conditions you want. And what we're really looking at here is, do you have a bunch of systems that are either underdamped or overdamped that have been out in your factory? And how can we very quickly let you see that those are the conditions and help you identify them and then go out and fix those? So that's kind of what it is. Oh, for PID, the first P is for proportional. I can't believe I forgot that. All right, so why does this matter? So really the idea is, I think this is probably the best phrase here, a stable plant is a sustainable plant and it's a healthy plant. So if I can have, just like in my car, if I can be always very smoothly going the right speed, that's gonna mean I'm gonna get there as quick as I can, right? If the speed limit is 65 and I'm always right at 65, that's perfect. If the speed limit goes to 70, I go right to 70. If it goes down to 55, I'm right there always. I get there quicker. And the smoother I can do this, the better it is for my engine, the better it is for my brakes, the better it is for everything in the car, right? The passenger holding a cup of coffee, right? The better I can actually be at just staying very smooth and right at the maximum optimal set point is going to be a happy plant. So that's really what we have here. So we have some examples. Like you could have a situation where you're going through here and you have your PID loops that are all over the place, right? So here's your set point. You're not that good. And then you have to stop the machine because you have problems, right? And then you've got to start up the machine again and everything else. So what we want to do is we first want to get your PID loops to be stable. So now instead of being all over the place, I'm trying to be at 65, I'm not 40 and 80, right? I'm basically right between, maybe, 60 and 70, right? I want to get it very stable. And then you can start getting closer to the actual ideal place. So some cases, this could actually mean something is, imagine you're trying to fill, let's just say, soda bottles. And for the soda bottle, you need to be at least 12 ounces. If you don't have very good control of your filling, right, and sometimes it's plus or minus an ounce, you've got to say, well, if I can never go below 12, right, and I'm plus or minus a whole ounce, now sometimes I'm going to be at 13, and I'm always going to be between 12 and 13. So in that case, you're actually throwing away like 8% of your product, right? Or 5% of your product because you're always overfilling because you can't get the control perfect. Now imagine if you could always get it within 0.1 ounces, now you could always fill right to 12. And the worst case scenario would be 12.1 ounces, but basically you'd still meet your spec and you wouldn't be giving away all of this extra product just to make sure that you're meeting your spec. And that exact same analogy happens with all of these things. If you could know that your product quality would be great, you could get your batches done quicker, You could have higher yields, less rework, right? So the idea here is the better I am at controlling my process, the better my product, my machine utilization, and everything else will be. All right, so here's all of the different things that control loops actually end up helping with. So a lot of these things come down through plant throughput. Again, if I'm running as fast as I can and I'm not having downtime and I'm getting good quality, I'm going to produce more with my plant in an 8-hour shift or a 12-hour shift than I will without this. So the smoother my plant runs, the more optimally and the more in control it runs, the better I'm going to have for throughput. The same thing for product quality. If your oven at home, if you set it at 350 and it's sometimes 300, sometimes 400, sometimes the chicken's going to come out of there burned. Sometimes the chicken's going to come out of there undercooked. If you know you're dead set at 350 every time, your chickens are going to come out of there perfectly cooked every time. And it's no different here with your process monitoring. Operational costs, the same thing. If I can run my machine for less hours and I can have less scrap and waste, my cost per ton, my cost per unit is actually going to be better. And then obviously reliability and safety, right? If I'm sitting here running my car and it's super inefficient and I'm slamming on the accelerator and slamming on the brakes all the time, right? This is going to be more dangerous driving, right? And it's also going to be harder on the equipment, which means the maintenance or safety related issues with maintenance are going to be higher. So really this stuff does, a smooth plant is really a good plant, and it affects all of these buckets of value to help your factory run with less drama and more throughput. So here's some of the reasons why we have this control loop performance monitoring. And some of these are actually, pretty obvious. So one of these things is that a lot of PID loops are put in automatic, like it's in cruise control. And then somebody says, you know what, like right now we're hitting a lot of traffic. I don't want it in cruise control. I want to basically take over manual control. And they start driving the car outside of cruise control. And then when they get onto the freeway again, they end up leaving it in manual mode, right? So they basically are like, I'm driving the car and I'm just going to put that valve at 30%, whatever it is. And they don't let it go back to the control. But if in a perfect world, those controls and your PID loops are set up correctly, your plant is going to run more efficiently, and there's not going to be someone on a coffee break who forgets to change the valve position. It's just going to happen all the time automatically. The other thing is, you're obviously exceeding limits. So this could be limits for quality. This could be if you have a temperature or pressure, you could be exceeding those limits, maybe making something go outside of safe operating parameters or things like that. That's another thing. The other thing that also happens with PID loops, and sometimes you have to see this, is sometimes I might have some equipment out there, like sensors that are out of calibration, or actually the thing that I have, the manipulated variable, like imagine you have a valve that's too small, so that even if I open that valve up 100%, it can't feed enough gas to keep 60 PSI. So sometimes you don't know that at the beginning, but as your process changes or something else goes on, you're going to end up noticing that, I've actually got to change that. If I don't have a big enough heater, no matter what, even if I turn on that heater 100%, I'm still not able to get to the new set point in the oven quick enough. If I don't have a big enough exhaust fan, I can't get there. If I don't have a big enough pump, there's no way I can actually keep that flow rate going, given the diameter of my pipes and stuff like that. So obviously being able to look for things like that you can't actually, you don't have the right equipment out there for your PID loops. All right, so I've got a couple of use cases here, and then I'm going to save some time here to get into a demo. So basically, this is a use case here where someone was looking before, and they were looking at their error, and then they were actually looking at their set points. They're looking at their set point. You can see here, they actually had a whole bunch of error. And this gets pointed out by our software. They say, you're seeing a whole bunch of error here. What happened is that they looked into it. They said, well, my PID parameters and the PID loop is actually going fine. What actually ended up happening was I actually had to do some replacement of a damper, and I had a sensor that was out of calibration. So basically they went through and figured out, you know what, the PID loop was fine, the settings were fine, the controller was doing what it was supposed to do, but basically the equipment needed maintenance because it wasn't working correctly, right? And I had a sensor that was telling me the wrong value. and those two things combine. So as soon as they actually change that, you can now see this error is basically sitting very low. So basically I have very little fluctuation. So if I'm trying to be at 65, I'm right at 65 or 66 or 64, but I'm not sitting there at 80 or 50. And really, hitting financial throughput metrics. Another one here that's kind of interesting is this one here is showing the status of PID loops in this factory. So they're saying in wave 1 here, what they actually had here is in auto or performance mode, right? So it's starting at about 55%, but also this machine was in shutdown mode 37% of the time at the beginning. And then it was in manual mode, meaning somebody said, I'm taking this out of PID control and I'm going to manually adjust things. And it was down here. And as they started doing this control loop performance monitoring, you could see they were actually going through and looking at the system and basically adjusting it. And they got all the way up to about 80% of the time now it was running, and only about 12% of the time was it not actually running. And then they actually stalled the project and they stopped monitoring. And you can actually see that everything stayed the same. It basically stayed at 80%, right? And it stayed at about 12%. Then they started up the project again, and it went from 80 to 84%, and it kept dropping the actual amount of time the machine was in shutdown mode. So basically, the idea here is this is part of continuous improvement. If you do it, you'll get performance increases. Maybe you'll find out that your equipment's not right. Maybe you'll find out your PID loops aren't right. But then what ends up happening is if you stop doing that, you'll keep the same performance, right? And maybe things might even start to degrade. But then if you stay on this as continuous improvement, you'll continue to get out those improvements as you go through. And kind of here is one last example. This is a mine that was in South Africa. And really what they ended up doing is they basically found out that the mine here had some valve instrumentation issues, and they were running in manual mode a lot. And what they wanted to do is make it so that the operators actually had more confidence in the PID loops because they were actually getting tuned and they were getting monitored, and they weren't actually seeing as many errors. Another reason why, before I get into the demo here, this is really, really important is because a lot of times you might have a special little PID loop controller that somebody does on the instrumentation side. Sometimes you might have a VFD that does PID loops in it. Sometimes you might have PLCs that have PID loops. Sometimes you might have DCS systems that have PID loops. The thing is, those are all coming from all of these different types of controllers, and it's really hard to get a good universal view of all of the PID loops that are going on in your factory. And that's really what we do here. We actually monitor all of those coming from those different types of PID controllers and actually pull those into one dashboard so you can monitor them all and then still go back to your instrumentation and process engineering team and say, hey, I'm noticing this loop isn't working well, and I want to basically, discuss it with you and show you what we're seeing. Let me quickly get into the demo here. Okay. Are you seeing my new screen? Okay. So we have a couple of things here that we are showing at a high level. One is sensor health, actually monitoring your sensors, alarm patterns, looking for alarm patterns. This is the one we're looking at, closed loop monitoring. If I actually start this demo here, I'll actually show you very quickly. I don't have much time, but I'll show you a little bit about what this looks like. So here's looking at a bunch of your loops that you can actually see over time, right? So here I'm looking at 7 days. It's actually looking at what is my performance like for these loops that you can actually see, right? You can actually see that they're about 30 or 40%. And if you actually wanted to, I could look at any one of these. So if I look at furnace 1, I can see how it's performing. You can actually see here, how are all of my loops performing at the bottom? And I'll actually go into some details here, which is kind of cool. So if I actually go in here to furnace loop 1, maybe I'll go into, let me see, yesterday's day shift, right? I can do a longer period of time if I wanted to. But you're actually going to get to see here, I'm actually looking at my set point as this green line in the middle. My blue lines are the error around that set point. And then your actual process variable, this would be my value I want to see. And then this manipulated variable is actually what I'm adjusting. This could be the accelerator or the heater or whatever else. So you can see that something happened here And then when my set point changed, you can see that it actually came down and did pretty well. So there was some error here that we saw. If you actually look at furnace loop 2, you can actually see that this had a very different profile. So this basically had a lot of overshoot, and then it basically took a long time to come back, right? So this was very fidgety. The accelerator worked great, the brake didn't work so great, right? So this is where you can kind of see how that's working and what's going on with that loop. And you can go back through here, and this is showing you furnace 3. This is another condition, right? So here's one. This was actually pretty good, right, coming through. So basically, this is a way to show you all of the parameters of how am I doing. And then when you start highlighting which loops are not working as well, that's when you can start bringing in your instrumentation teams and your other teams to actually go through and start troubleshooting the problem and getting those loops figured out or getting the equipment maintenanced so your plant can run more smoothly. So I know we're getting late, so I think we'll go to Q&A at this point. Arnie, are there any questions?
I'm seeing a couple questions, but this is a time for the audience today to ask any more questions you may have. We have a couple more minutes. If not, I'll get started on the first question. Okay. Will this work with any brand of PLC?
Yeah, so this basically works. It sits on top of all of your controllers. So as long as that data, if we can get the data into our system via OPC or MQTT or Modbus, whatever it is, it'll work with PID loop controllers. It will work with VFDs that have PID loops. It will work with PLCs. It will work with DCS systems. Anything that's doing your PID control, yes.
Okay, thank you. And then the other question is, how do I purchase this? Is it part of my SCADA license?
So it's tricky. So if you have a standard SCADA license today, it's not included. You can buy our product called C-Sense, which is our analytics product, which basically has this ability to do this. Some of those other things I talked about, alarm pattern recognition, sensor health, or control loop monitoring. It also does advanced process control. So you can actually purchase that. We actually have a new offering called SCADA Ultimate. And if you do get that, then you can easily have your SCADA tags go into Historian, and then you also get access to this. So you can talk to your salesperson about going to SCADA Ultimate, which will give you access to this. And again, it's really nice because it sits up that control layer. And if you do have any sensors or any control loops or anything else that are not working correctly, it'll flag it. And maybe your team hasn't seen it yet. And then you can go down and say, hey, what's going on with this sensor? I think it's out of calibration. And you can go back and highlight those items.
Makes sense. We have 1 more minute. Any more questions from the audience? You can use the Q&A tab to your right. All right. If we have no more questions, we will end the webinar today. Thank you, Will, again for this great presentation. We will be sending it to you as a recording after this call. And we have a quick survey that I mentioned in the end for any feedback you have on this webinar. And with that, I think we can close it today. Thank you, Will.
Thank you.